All right, folks, this is the lecture on section 7.8, improper integrals, day 1. Let's dive right in here. The definition of an improper integral falls into one of two ways. Doesn't even make sense, Jenkins. Are you even reading what you're writing? An improper integral falls into one of two categories. A type 1 improper integral has infinite limits. So you might see something like the integral from 3 to infinity of f of x dx, or negative infinity up to 0 of g of x dx. It's these improper integrals. It's these infinite limits that make these improper integrals. Or, an extreme case might be something like negative infinity to positive infinity of h of x dx. And we're going to talk about what that means in just a little bit. The second category, the type 2 integral that is improper, is integration over an interval containing a discontinuity. So an example of that might be something like this. I'm going to have to give you a specific function here, but maybe something like the integral of 1 over x from negative 1 to 1. It looks pretty harmless, but the problem here is we're integrating over the interval negative 1 to 1, which contains x equals 0. Or more importantly, the relevant domain of 1 over x is negative infinity up to 0, union 0 to infinity. And so when we take the intersection of those, we should be integrating from negative 1 to 0, union 0 to infinity. Another example might be something like the integral from 0 to 1 of the natural log of x dx. Again, the natural log of 0 is undefined, as is above. 1 over 0 is undefined. So we have these discontinuities, and we're trying to integrate right across them as if they weren't even there, and that makes them a type 2 improper integral. So note, before we get started here, both types of improper integrals may require L'Hopital's rule and may depend heavily on your ability to use L'Hopital's rule, as we'll see in some of the coming examples. You may wish to review this before attempting several problems in this section. So just keep that in mind. If you're a little rusty on L'Hopital's rule, this section uses it pretty heavily, so you're going to have to go back and review that. Let's talk about what a type 1 improper integral is for real. So we're going to let f of x be a continuous function over the interval a to infinity. And likewise here, maybe negative infinity to b as our counterpart to this definition, where a or b is any real number. Then how do we deal with a type 1 improper integral? Then the integral from a to infinity of f of x dx, well, what does that mean, right? Like, gee whiz, if this is the x-axis and the y-axis, and maybe here's a, and positive infinity is way at the end here, and we have this function, f of x, I guess what we're really talking about here is how much area is underneath that curve all the way out to infinity. And your gut reaction might be an infinite amount of area. But as we're going to see, that's not always necessarily true. So how do we deal with this? Well, in a pretty straightforward manner, actually, what we're going to do is we're going to take the limit as b approaches infinity and take the integral from a to b of f of x dx. So essentially what we're doing is we're going to take a limit of a sequence of integrals, so to speak. That is to say, we're going to go from a finite number to a finite number, evaluate that. So hopefully we can find the antiderivative. and that'll be capital F, the antiderivative evaluated at B, minus capital F, the antiderivative evaluated at A. And then the question becomes, what is this limit? Likewise, as I have here in red, we can do the same thing for negative infinity up to B of f of x dx. So if we have a lower limit that is improper, negative infinity, we can kind of deal with this the same way and look at the limit as a approaches negative infinity of the integral from a to b of f of x dx, which will translate into the limit as a approaches negative infinity of capital F of b minus capital F of a. So the integration's not supposed to be the problem. The problem is supposed to be evaluating your result, your antiderivative at the endpoints. And that's where the limiting process comes in. So in either case, this is what we're going to be doing. And in an extreme case, we might go so far as to do something like the integral from negative infinity to infinity of f of x dx if it's continuous, if f of x is continuous from negative infinity to infinity, then what we can do is we can actually break up this integral anywhere we want. Typically we break it up in the center at 0 and do negative infinity to 0 of f of x dx plus the integral from 0 to infinity of f of x dx, and then evaluate each one of these using the above techniques. Right? So in the extreme case where both of your limits are improper, you can break this function up. It doesn't even have to be broken up at 0. This could have been broken up at, A and A. It really didn't matter. So it looks kind of weird. A and A. Anywhere in between. So basically break your interval in half and do the left side and the right side separately and add them together. Okay, let's talk about terminology. If the integral from a to infinity of f of x dx, or the integral from negative infinity to a of f, I should say to b there, b dx, or the integral from negative infinity to infinity of f of x dx, which results in limits, exists, i.e., is equal to a real number, we say the integral converges. If the integral from a to infinity of f of x, or any one of its counterparts above, does not exist, we say the integral diverges. So there's some terminology, and it's very black and white. It either converges or it doesn't. And when I say exist and does not exist, I'm really referring to the resulting limits here, folks. If these limits exist or not, because inside every improper integral is a limit. So let's take a look at some examples. Let's use some of our terminology and get started in the next video.